Inside a windowless fabrication hall in Hsinchu, Taiwan, machines the size of buses are placing individual atoms with a precision that borders on impossible, and what comes out the other end is quietly rewriting the limits of computing itself. Scientists and engineers at TSMC have just pulled back the curtain on a new generation of chip technology, and the details reveal something far stranger and more consequential than a simple speed bump. This isn't just a smaller transistor. It's a fundamental redesign of how electricity moves through silicon, how chips talk to each other, and how much computing power can physically fit inside a single package. And once you understand what's actually happening inside these new chips, you start to see why the entire AI industry is holding its breath waiting for them. For decades, the story of chip progress was simple to tell. Every couple of years, engineers found a way to shrink transistors a little further, cram a few billion more onto a sliver of silicon, and computers got faster almost as a matter of course. That story is now breaking down. Transistors have gotten so small that shrinking them further barely moves the needle on performance, and in some cases, it doesn't move it at all. So the engineers at TSMC did something unusual. Instead of only chasing smaller, they started chasing different. They redesigned how power itself gets delivered inside the chip, they rebuilt how multiple chips get physically stacked and glued together, and they even started experimenting with sending data using pulses of light instead of electricity. The result is a new node called A16, and the ideas packed into it are more radical than almost anything the semiconductor industry has produced in the last 20 years. Here's the part almost nobody outside the industry understands. Inside a normal chip, the wiring that delivers power to the transistors and the wiring that carries the actual data signals are tangled together on the same side of the silicon. That's been true since the earliest days of the microchip. As transistors have shrunk to almost nothing, this shared wiring has become a serious problem. Power lines and signal lines are now so close together that they interfere with each other, and there simply isn't enough physical room to make both work efficiently at the same time. TSMC's answer, built into the new A16 process, is to physically split them apart. Power delivery is moved to the back of the wafer on the opposite side from the signal wiring in a design the company calls superpower rail. Think of it like separating a building's electrical wiring from its data cabling instead of running both through the same crowded wall cavity. Suddenly, there's room to breathe. Power arrives more directly, with less resistance and less wasted energy, and the front of the chip is free to pack in more logic without the two systems fighting each other for space. This backside power delivery isn't just a clever engineering trick. It solves what insiders have started calling the power wall, the point where feeding a chip enough electricity and getting rid of the heat that comes with it becomes harder than actually shrinking the transistors. Advanced AI chips today can draw as much electricity as a small neighborhood, and getting that power to exactly the right spot on a piece of silicon, smaller than a fingernail, without frying anything nearby, is one of the hardest problems in modern engineering. By moving the power delivery network to its own dedicated layer, engineers have found a way to feed these hungry chips more efficiently, which matters enormously as artificial intelligence models balloon in size and demand more raw compute than anything that came before them. TSMC is targeting mass production of this A16 node in the second half of 2026, and the timing is not an accident. It lines up almost perfectly with the next generation of AI accelerator chips that companies like NVIDIA are racing to bring to market. Every major AI lab, every hyperscale data center operator, every company building the next wave of large language models is fundamentally bottlenecked by how much computing power they can get their hands on, and how efficiently that computing power can be cooled and powered once it's installed. A node like A16 isn't just an incremental refresh. It is quite literally the physical foundation that determines how fast the entire AI industry can move over the next several years. But the story doesn't stop at A16. Sitting just ahead of it on the roadmap is a node called A14, TSMC's most advanced transistor architecture to date, and behind that, a further refinement called A13 that shrinks the design even more while staying compatible with the same manufacturing rules. That backward compatibility matters more than it might sound. It means a company that designs a chip for A14 can migrate that same design to the more advanced A13 node relatively quickly, without redoing years of engineering work from scratch. TSMC has said A13 delivers roughly a 6% reduction in chip area compared to A14, on top of further gains in power efficiency and performance. A14 itself is expected to enter production in 2028, with A13 following about a year later. These aren't just numbers on a slide. Every percentage point of area saved means more transistors fit in the same space, which means more raw computational horsepower for the same manufacturing cost, which trickles down into everything from the phone in your pocket to the servers running the AI systems answering your questions right now. Alongside these headline transistor nodes, TSMC has also been quietly refining a chip technology called N2U, a variant of its 2 nanometer platform tuned specifically for balance rather than raw extremity. According to the technical details TSMC presented, N2U offers speed gains in the range of 3 to 4% at the same power draw, or alternatively, a power reduction of 8 to 10% at the same speed, along with a modest bump in transistor density. It's scheduled to enter production in 2028. What makes N2U interesting is what it represents strategically. Not every customer needs the absolute bleeding edge of TSMC's technology. Some need a proven, mature platform that offers strong yields and predictable performance for products that will ship in massive volume, from smartphones to laptops to the kind of high-performance computing hardware that doesn't always make headlines but quietly runs the modern world. Now here's where things get genuinely strange, in the best possible way. For most of computing history, making a chip faster meant making the chip itself faster. But engineers have hit a wall where the transistors themselves are approaching the physical limits of what silicon can do. So the industry's smartest minds have pivoted to a different question entirely. Instead of asking how do we make one chip faster, they're asking how do we combine many chips into something that behaves like one much larger, much more powerful chip. This is the world of advanced packaging. And it might be the single most important technological shift happening in semiconductors right now, even though almost nobody outside the industry has heard of it. TSMC's core packaging technology, called CoWoS, short for chip on wafer on substrate, takes multiple pieces of silicon, logic dies, memory stacks, and sometimes specialized chiplets, and fuses them together onto a single unified package. The scale of what's now possible is genuinely staggering. TSMC is currently producing packages built on a substrate 5.5 times the size of a standard chip reticle, and the company has laid out plans to expand that to 14 times reticle size by 2029, a package capable of integrating roughly 10 large compute dies alongside 20 stacks of high bandwidth memory, all working together as though they were a single piece of silicon. To put that in perspective, this is the physical infrastructure that lets an AI chip access dramatically more memory bandwidth than would ever be possible on a single monolithic die, which directly translates into faster training times and faster responses for the AI systems built on top of this hardware. And TSMC isn't stopping at CoWoS. Reports emerging from supply chain analysts describe a next-generation packaging technology, sometimes referred to as CoPoS, that could push these ultra-large packages even further, potentially reaching mass production in the second half of 2028. Early details suggest the process may use a temporary glass carrier during manufacturing, a material chosen because it offers extreme flatness and dimensional stability while the delicate silicon components are being assembled before being removed, so the final package returns to a conventional substrate. Analysts studying supply chain movements have floated the possibility that entirely new generations of AI accelerator chips could become early adopters of technology like this, given the industry's insatiable appetite for larger and larger packages stuffed with compute and memory. The broader point is unmistakable. Advanced packaging is no longer a side project or a niche specialty. It has become one of the most fiercely competitive battlegrounds in the entire semiconductor industry, right alongside the race for smaller transistors. There's also a piece of this puzzle that sounds almost like science fiction, but is very real and already entering production. TSMC has developed something called the Compact Universal Photonic Engine, or COUP, a technology that moves data between chips using pulses of light instead of electrical signals. Light doesn't generate the same resistive heat that electrical signals do over long distances, and it can carry vastly more information per second. By integrating this optical engine directly inside the chip package, rather than as a separate pluggable component sitting elsewhere on the circuit board, TSMC has managed to roughly double the power efficiency of these optical connections while cutting latency by a factor of 10. One of the first real applications is a 200 gigabit per second micro-ring modulator, a component specifically engineered to move enormous volumes of data between server racks inside AI data centers, where the sheer amount of information flying between machines has become one of the biggest bottlenecks in scaling these systems further. This co-packaged optics approach is expected to begin production in 2026, which makes it one of the more imminent breakthroughs on this entire roadmap. TSMC is also pushing forward with three-dimensional chip stacking, a technology called SoIC, which physically bonds chips vertically, layer on top of layer, rather than spreading them out flat across a package. The next iteration of this, pairing two A14 class chips directly on top of each other, is slated for production in 2029 and is expected to deliver roughly 1.8 times higher input-output density between the stacked layers compared to the current generation, stacking 2 nanometer chips together. Vertical stacking like this shortens the physical distance data has to travel between chips dramatically, and shorter distances mean faster communication and lower energy costs, which becomes exponentially more important as AI models grow into the hundreds of billions and eventually trillions of parameters. Zoom out for a moment, because the scale of what's happening here goes well beyond any single company's product roadmap. Industry analysts, tracking this technology symposium data, believe global semiconductor revenue could grow somewhere between 30 and 40% this year alone, an extraordinary figure for an industry this mature. And much of that growth isn't coming from selling more chips, it's coming from the chips themselves, commanding dramatically higher prices, driven heavily by surging memory costs and premium pricing on the highest-end AI accelerators. Some projections now suggest the global semiconductor market could blow past $1.5 trillion by 2030, with artificial intelligence and high-performance computing together accounting for more than half of all demand, dwarfing smartphones, automotive chips, and the broader Internet of Things combined. Every one of the technologies described here, the backside power delivery, the shrinking transistor nodes, the massive advanced packages, the light-based interconnects, exists specifically to feed that demand. And TSMC is not resting on any of this. Reports indicate the company has already begun early planning stages for a 1 nanometer manufacturing process, a scale so small that individual features on the chip would measure only a handful of atoms across. To support this future roadmap, TSMC is reportedly planning to construct as many as 12 new fabrication facilities, covering everything from current 2 nanometer production down to future 1.4 nanometer nodes. But full-scale 1 nanometer commercialization faces real obstacles. Land acquisition delays affecting a major planned expansion in Taiwan mean that true mass production of 1 nanometer chips likely won't arrive before 2030 or 2031 at the earliest. It's a reminder that even the most advanced technology on the planet is still bound by the very physical realities of construction, land, and infrastructure that govern any large industrial undertaking. What makes all of this particularly fascinating is the competitive backdrop it's unfolding against. Intel has been racing to reclaim manufacturing leadership with its own 18A process, which actually brought backside power delivery to market slightly ahead of TSMC, a genuine milestone for a company that spent years playing catch-up. But industry observers widely view TSMC's implementation, arriving with A16, as the more refined and mature execution of the same underlying idea. Samsung, meanwhile, has faced its own struggles, with reports suggesting its 3 nanometer gate-all around transistor yields have lagged behind TSMC's, prompting some customers to shift their 2026 and 2027 chip orders over to the Taiwanese foundry instead. This is a business where trust is earned in yield percentages and reliability metrics measured over years, not marketing slides. And right now, the data is telling a fairly clear story about who currently holds the advantage. There's a wider context here, too, that goes beyond corporate competition. As data centers packed with these next-generation AI chips multiply around the world, their electricity demands are becoming a genuine strain on power grids. Some estimates suggest that by the end of this year, AI-focused data centers could account for nearly half of all electricity consumed by data centers globally, a staggering figure that ties directly back to why innovations like backside power delivery matter so much. Every percentage point of efficiency gained inside the silicon itself translates into real, measurable reductions in the energy required to run these systems at a planetary scale. This is no longer just a story about faster phones or snappier laptops. It's a story about the physical infrastructure of energy and computation that increasingly underlies how modern society functions. From the recommendation engine, suggesting your next video, to the AI systems being used in scientific research, medicine, and defense. To really appreciate how big a departure this is, it helps to understand what a nanosheet transistor actually is, because that's the underlying architecture powering nearly every one of these new nodes. For years, chipmakers relied on a design called FinFET, where the electrical channel of the transistor stood up like a thin vertical fin, with the gate wrapped around 3 of its 4 sides. It was a clever solution in its time, but as transistors kept shrinking, the fin design started leaking current and losing control over the electrical signal passing through it. TSMC's nanosheet architecture solves this by stacking horizontal sheets of material on top of each other and wrapping the gate completely around all 4 sides of each sheet. That full wraparound gives engineers far tighter control over the flow of electricity, which means less wasted power, less unwanted leakage, and the ability to keep shrinking transistors without everything falling apart electrically. Every node discussed here, from A16 down through A14 and A13, is built on this nanosheet foundation, refined and iterated generation after generation. It's also worth understanding just how differently TSMC treats different corners of the chip market, because the company isn't only chasing the absolute cutting edge. Alongside its most advanced nodes, TSMC has continued refining specialized processes for industries that need reliability and specific performance characteristics far more than they need the smallest possible transistor. Its N3A process, part of a program that let automotive customers begin designs years in advance, entered production in 2026, with more than 10 separate automotive products already built on top of it, aimed at making vehicles smarter, more efficient, and safer through more capable onboard chips. TSMC has also pushed high-voltage technology into advanced manufacturing for the first time with a process called N16HV, purpose-built for display drivers. In smartphones, it increases gate density by over 40% while cutting power draw by more than a third compared to the previous generation. In near-eye displays, the kind used in smart glasses and emerging wearable devices, it can shrink the physical die area by 40%, while reducing power by a fifth or more. These aren't the chips that make headlines, but they quietly determine how long your devices last on a single charge and how sharp the screen looks in your hand. None of this progress happens by accident, and none of it happens quickly. TSMC didn't become the company sitting at the center of the entire AI supply chain overnight. It pioneered something called the pure play foundry model back in 1987, a business built entirely around manufacturing chips designed by other companies rather than designing and selling its own branded products. That decision, made nearly 4 decades ago, is precisely why companies like NVIDIA, Apple, and AMD can focus purely on designing groundbreaking chips, while trusting TSMC to actually manufacture them at a scale and precision that would be almost impossible to replicate independently. Every technology described here, the backside power delivery, the massive multi-die packages, the light-based interconnects, exists within that same foundational business model, one built on decades of accumulated manufacturing expertise that competitors have struggled for years to match. The competitive stakes extend well beyond bragging rights over transistor counts. Reports circulating among supply chain analysts suggest that NVIDIA's future generation of AI accelerator chips, chips that reportedly carry the internal code name, Feynman, could be among the earliest adopters of TSMC's next wave of advanced packaging technology. If that plays out, it would mean the AI hardware powering the next generation of large language models and AI reasoning systems is being architected specifically around packaging techniques that don't even exist in mass production yet. That's an extraordinary vote of confidence, and it underscores just how tightly intertwined chip design and chip manufacturing have become at the frontier of artificial intelligence. A brilliant chip design is worthless without a manufacturing partner, capable of physically building it at the scale, yield, and reliability the market demands. And right now, for the most advanced AI silicon on the planet, that partner is overwhelmingly TSMC. It's also worth sitting with just how much all of this has changed in a remarkably short window of time. A handful of years ago, backside power delivery was a research concept discussed mostly in academic papers and conference presentations. Chip on wafer on substrate packaging existed, but nowhere, near the staggering 14 reticle scale now on TSMC's roadmap. Co-packaged optics that place light-based data transfer directly inside a chip package, rather than as a bolt-on accessory, were barely more than laboratory demonstrations. Today, every one of those ideas sits on a concrete production timeline, with dates attached, customers lined up, and billions of dollars of capital investment already committed. That's the real story hiding inside the technical jargon and the process node names. The pace of change inside chip manufacturing has accelerated dramatically, driven almost entirely by the voracious appetite of artificial intelligence for more computing power than anyone imagined would be necessary just a few short years ago. So when people say scientists have finally revealed what's really happening inside TSMC's new chips, this is the honest answer. It isn't a single dramatic breakthrough. It's a coordinated, almost symphonic re-engineering of nearly every layer of how a chip is built, from the way power reaches individual transistors to the way separate pieces of silicon are physically fused together into something larger than any one chip could ever be, to the way information itself moves using light rather than electricity. Each piece on its own is impressive. Together they represent the physical foundation that will determine how far artificial intelligence can actually go over the next several years, and how much energy the world will have to spend to get there. The chips being described on roadmaps today won't even reach mass production until 2026 through 2029, which means the true impact of everything revealed here is still ahead of us, quietly being built right now inside cleanrooms in Taiwan, waiting to reshape the technology all of us will depend on tomorrow. Consider what this actually means for the device sitting in your pocket, or the laptop on your desk, or the AI assistant you might be talking to a year or two from now. Every one of the breakthroughs described here eventually filters down from billion-dollar data centers into consumer hardware. Backside. Power delivery, first perfected for the most demanding AI accelerators on the planet, will eventually show up in the processor inside a mainstream smartphone, quietly extending battery life without you ever noticing the underlying reason why. Advanced packaging techniques, first developed to stack high-bandwidth memory next to AI compute dies, will filter down into more affordable laptops that can suddenly run sophisticated AI models locally without needing to send your data to a remote server at all. This is how semiconductor progress has always worked. The most extreme, most expensive innovations get proven out first at the absolute frontier, where companies are willing to pay almost anything for an edge, and then, over a handful of years, those same ideas become affordable enough to appear in ordinary consumer products. There's also a geopolitical dimension to all of this that's impossible to ignore. TSMC's dominance in advanced chip manufacturing means that a huge share of the world's most critical computing infrastructure, the silicon underpinning artificial intelligence, military systems, financial markets, and telecommunications networks, is concentrated on a relatively small island in East Asia. That concentration has made TSMC's continued technological leadership a matter of intense strategic interest well beyond the technology industry itself, shaping trade policy, export controls, and enormous government-subsidized investments in domestic chip manufacturing capacity from Washington to Brussels to Tokyo. Every new node TSMC announces isn't just a corporate milestone. It's a data point in a much larger conversation about who controls the physical infrastructure that the next era of artificial intelligence and arguably the next era of global power will be built on top of. What makes this moment particularly remarkable is the sheer density of innovation happening simultaneously across so many different fronts at once. In almost any other era of semiconductor history, a single one of these breakthroughs, backside power delivery, or 14 reticle scale packaging, or co-packaged optics moving data at the speed of light, would have been considered the defining technology story of the year on its own. Right now, TSMC is advancing all of them at the same time, on overlapping timelines feeding directly into each other. A chip built on the A16 node with backside. Power delivery will very likely be packaged using the next generation of CoWoS technology, connected to other chips using co-packaged optics, and potentially stacked using three-dimensional bonding all within the same physical product. These aren't separate innovations happening in isolation. They are converging into unified systems that behave less like a single chip in the traditional sense, and more like an entire miniaturized data center compressed into a package you could hold in the palm of your hand. And that, ultimately, is what scientists have really uncovered when they pull back the curtain on TSMC's newest chips. Not a single dramatic discovery, but a coordinated leap forward across power delivery, transistor architecture, three-dimensional integration, and optical communication, all arriving within the same narrow window of time, all engineered specifically to satisfy an appetite for artificial intelligence that shows no sign of slowing down. The machines, placing individual atoms inside that windowless fabrication hall in Hsinchu, aren't just building faster processors. They're quietly constructing the physical foundation of whatever comes next, and if the roadmap TSMC has laid out actually holds, the next several years are going to look very different from anything that came before them.